Well, thank you, Sam. I want to make sure everybody can hear me. Is that all right up there? Okay. It's really quite an honor to be invited to give a talk in a series that's had such incredibly prestigious scientists, so I'm really proud of that, and thanks to Monash and for Sam for inviting me. So I got the bug of astronomy pretty early, but I never really thought that it was something you could actually do as a profession. I never met any astronomers. I never got to go see any, give talks or anything as I was growing up. But what I did see were stars in the sky, and I used to make up my own little constellations. And I would see the Milky Way galaxy across the sky a couple times. You have to go pretty far out of the city to be able to see that. So I'd actually like to ask, how many people have seen the Milky Way in the night sky? That's pretty good. It's a sad response when I ask that to undergraduates. It's getting a lower and lower fraction of people who have actually seen the Milky Way. So when I was young, I used to see this thing up in the sky, and it just fascinated me. It really made me wonder why you see kind of tiny little dots everywhere, but then in this one spot of the sky, you see all of this fuzziness, a bit of extra glow, and then kind of dark regions. It just fascinated me, and so ultimately what I do is try to study how that came to be, how the Milky Way is there, and why does it look the way that it does in the sky. So let's see if this technology works. There we go. Here's another image of the Milky Way. This one's from the Southern Hemisphere. You all are very lucky in the Southern Hemisphere. You get these large and small Magellanic Clouds, their own little galaxies. I love them. This is in Chile, this Patagonia mountain region, and this is Comet McNaught that came in 2007 or so. So what we see here is the Milky Way galaxy, and you can see that there's a glow created by all the stars. There's hundreds of billions of stars in the Milky Way galaxy, so all of those things glow collectively. And then there are these little dark spots. So those dark spots are actually clouds of dust and gas that are blocking the light from the stars behind them. So just like on a cloudy day here, we can't see our shadow anymore. These are actually blocking all the light that's coming from behind them. Another fascinating thing, this is the Coalsack Nebula here. You can kind of see the Southern Cross and the pointers. The Aboriginal cultures of Australia have stories about these dark spots in the sky. So this is the head of the emu, and the emu stretches all the way across the Milky Way. And I haven't heard of any other cultures or any other people around the world that actually have stories about the lack of stars in certain spots of the sky, and I just find that fascinating. So now we have to ask, why does the Milky Way actually look like this? Why is it a big line across the sky? That's not really the image that we have of galaxies in our mind. We see these nice, gorgeous spiral arms in these Hubble images. So we live inside of the Milky Way galaxy. If we jumped inside of a rocket and flew way far away from our galaxy, something that we might see is this. This is an unromantically named galaxy, NGC 4565. They have kind of phone numbers instead of real pretty names. It's because there's so many of them, we kind of run out of names. So if we zoomed out of our galaxy, we might see something like this. And this makes it a lot more clear why you see these dark spots. You really can tell here that it's the clouds of dust that are blocking all of the light. Here in the central region, we have something called a bulge, where there's a big collection of stars that are kind of a sphere, a little ball, and then we've got this disk out here. So the Milky Way galaxy actually lives outside in one of the disks. So this is this edge-on view of the galaxy, and if you look at it from the top or the bottom, then you start to see these really nice spiral arms, which is the image that we have, the iconic image of a galaxy. So we have the central bulge region. It's very bright. There's lots of stars there. You can see it glows a little bit orange. There's the spiral arms that are out in this disk. And there's globular clusters that go all the way, that orbit all the way around here. So these are big collections of lots of stars, hundreds of thousands of stars stuck together. Sorry, I'm kind of new to this thing, so it's messing with me here. The galaxy is about 120,000 light years across. So it takes light 120,000 years to travel from a star on this side of the disk all the way over to that side. That's a long time, and it's a long way. And this is only one galaxy. Let's see, what else do we have? We have a supermassive black hole in the center of our galaxy, and almost every single galaxy we've ever looked at has a supermassive black hole in the center. That's kind of fun, just fun to say. It's actually what we use we say supermassive black hole. It's not named after the Muse album, if anybody knows that band. Let's see, and this is where our sun lives. So our sun is about 26,000 light years out, away from the center, away from that supermassive black hole. Now the sun, I'm going to specify the difference between a galaxy and a solar system, because a lot of people that I talk to get a little bit confused by these. So the solar system is our system around the sun. So sol is the Latin word for sun. So it's based on the sun, and it's all the planets that go around the sun. That's the solar system, and there's comets and asteroids and things. And that whole system, this sun, the entire thing, orbits around the Milky Way galaxy. So our sun and our system, the Earth, takes about 1 year to go around. The sun, the entire solar system, takes about 250 million years to go one time around the Milky Way galaxy. That's a long time. It's a long year, if you will. And you can imagine that because of that, we don't really see in our lifetimes any significant change in one galaxy. So there's ways we can get around that later, as I'll describe.
Can I ask a question?
Sure.
Why does the dust clouds settle in the plane of the galaxy?
Oh, good question. So ultimately, the answer is conservation of angular momentum. So if a galaxy forms from a big initial gas cloud that's spherical, it starts to spin. This is just sort of a natural thing. All these systems start to spin, and as it spins, it slowly settles into this disk and gets flatter and flatter and flatter. So you've got still this dense region in the center, but then you've got this big disk of dust and everything. It's the same thing that happens when planets form. So you've got a cloud of gas, and a star starts to form in the center. And all the rest of the gas, it just kind of slowly starts to spin and settles into this disk. And from that disk is where the planets form. So they're all orbiting in one disk around that central star. So that's a much smaller system. Our galaxy is much bigger, but it's the same principle. As much as we know, there are details that we don't quite understand still. Okay, so this is what our galaxy looks like. And this brings me to one of my favorite little quirks of the universe. As I said, on the solar system and the galaxy, we've still got conservation of angular momentum, completely different size scales, but the same physics is at work. The same thing happens in lots of other regions of our universe. So on different scales, the same physics cause the same sort of shapes or phenomena to happen. So here we've got two, see, this thing is driving me crazy. I'm going to have to not use it so that I don't give away my punchlines. So these two things look relatively similar. I'm going to try to do this. We'll see if it works. I don't know. They look pretty similar. The one on the right is the Whirlpool Galaxy. It's actually an image taken with a radio telescope, known as M51 as well. This one actually has a real name. And then the one on the left is Hurricane Hugo, which was a pretty big, devastating hurricane that hit the U.S. in the 1990s. And this was taken from a satellite above the Earth. So you can see this nice spiral arm sort of structure, even though some of the detailed physics of what causes a hurricane is completely different than a galaxy, but we still have this conservation of angular momentum, density waves, that cause these spiral arms and spiral structure. Also, as water's going down your drain, you see that nice spiral structure. It's everywhere, all over the universe, based on the same fundamental physics, just on different scales. This is another image of the Whirlpool Galaxy, one that you might be a bit more familiar with. While spiral galaxies are absolutely gorgeous, they're certainly not the only kinds of galaxies that exist out there. So this is Edwin Hubble's classification scheme. A lot of people call it the tuning fork, because you've got two little forks here. So we've got the spiral galaxies that I already talked about. You can see these nice spiral arms shooting out here. Down here on the bottom, it's the same spiral galaxy, but they also have a bar in the center. So the spiral arms shoot out from the bar. And as we go towards the left, you start to get more and more of a contribution from this central bulge region and less contribution from the disk. And as we go farther and farther to the left, you see that the spiral arms aren't really very obvious anymore, to the point where we get to these ellipticals, and it's almost all these round, kind of cigar-shaped things down here, and they get rounder and rounder and rounder. So they're just these huge spherical balls. The stars are moving around in all sorts of different directions. But there's really no evidence of a disk anymore when we get to this edge. Now, galaxies come in everything in between, but the majority of what we see fit onto this tuning diagram pretty well. So this was first discovered by Edwin Hubble, or at least first put forth, published by Edwin Hubble. This is Hubble here, smoking his pipe. He was pretty notorious for always having his pipe back in the early 1900s. And here he is with Einstein, maybe one of the few times Einstein actually ever looked through a telescope. Here's Hubble with his pipe in hand, very good for the optics of the system, of course. They didn't care about those sorts of things back then. So what Hubble did in the early 1900s was he sat at this telescope. This is the 100-inch Hooker telescope in Mount Wilson in California. And for almost 40 years, early in the century, this was the... Is my microphone just turned off? Yeah. I'm a bit of a loud talker, so... Okay. Are we back? Yep. Okay, so this telescope in California was the biggest telescope on Earth for about 40 years. So it was a pretty sizable one. And what Hubble did was he actually sat out all night long, very cold, long nights, and on photographic plates took images of different things around the sky. So these photographic plates, these are these big pieces of glass that are 2 feet by 2 feet, and you actually stick them into the telescope and you expose on it just like you used to with film, and then you'd have to take it to a room somewhere in this dome, and you would develop it just like you do with all the chemicals and everything. And then you would see what you get. So this is an example, a zoom in of one of these photographic plates that Hubble looked at. I'm sorry, this keeps coming up. So this is actually the Andromeda galaxy. It's a zoom into the center. The Andromeda kind of goes way out, but this is the inner region here. And what Hubble did was he would look at these galaxies over and over again, looking for things that change, looking for nova, so exploding stars. And when he would find one, really, I might just not use it anymore. So when he would find them, he would mark them with a nova. So he had really good pattern recognition. He was able to look at these images and then wait for a couple months or a year and look at this again, and then he would see a new star come up. It would be a star that explodes and gets really bright for a few months, and then it would fade away. So can everybody hear me if I don't use this thing? Okay. Yeah. Okay, good. It's not one type of technology, it's another. So he pointed out all these novae on here. The date here is 1913, 23? Yeah, 23. So he kept seeing these things, but then he looked at Andromeda again, and he noticed this one here, which he first marked as a novae. But then he went back to it sometime later and realized that it got bright again. And stars don't explode twice. Once you explode, you're pretty much gone. So he wondered what this was and realized it was a star called a Cepheid variable star. So he marks far and gets very excited. So he found a Cepheid variable star in Andromeda in the 1920s, and at this time, remember, we thought that the entire universe was within the Milky Way galaxy, so it's about 100,000 light years across. So he discovers this Cepheid variable star in Andromeda, and he's able to use this method derived from Henrietta Leavitt, who was one of the first actually recognized female astronomers that we have on record. She came up with this method to determine the distance to the star. So Cepheid variable star is one that kind of puffs up and shrinks down again. And the regularity that it does that in, it could be a few days, it could be a few months, it's based on how bright it is. So if you know how physically bright it is, based on how frequently it gets bright and dim, and you know how bright it looks, based on how far away, that you can determine how far away it is. So he did this to figure out how far away the Andromeda galaxy is, and instead of being just 100,000 light years, it's actually a few million light years away. So all of a sudden our universe goes from being just the Milky Way galaxy to being huge. And all of these little fuzzy things in the sky aren't just little nebulous gas balls. They're actually entire galaxies with hundreds of billions of stars in them. So he starts looking at these things and then notices they have different shapes and comes up with his tuning fork diagram. And all of a sudden, the 1920s, our universe just expands. It's a pretty exciting time. So Hubble has these wonderful breakthroughs in the 20s and 30s. So later in time, we name a telescope after him. The Hubble Space Telescope, you may have heard of it, and it's when they first launched it, I was kind of young, but I still remember it. And I remember reading in the newspaper, Hubble needs glasses. because they didn't make the mirror quite right. It had a little bit of an astigmatism. So they ended up having to go up and put a big monocle on it to fix it, and then everything came in focus. But I remember thinking as I was reading the paper, well, that was dumb. Why did you do that? But the images that came back after they fixed it were pretty spectacular. Okay, so now we have this wonderful space telescope orbiting up in space. You want to be up in space because you're outside of the atmosphere. I'll show you a little bit later. The atmosphere absorbs some of the light that comes through it, so you just lose that information, essentially. It really shakes up all your photons and makes your data a bit harder to understand. Not impossible, obviously. We still build telescopes, but they're a lot easier, better, if you can put them in space. Just a little more expensive. So we've got this fabulous telescope up in space. What do we do with it? That's not a trivial question. So what astronomers decided to do with it was to look at a spot in the sky. They said, let's look somewhere that, to every other telescope, looks completely empty. So they looked at a region, doesn't show any objects in any other telescopes that we've ever used. They looked at it for 400 orbits. So Hubble went around and looked at it for about 1 million seconds, and they added up all the photons that they received from this tiny little pinprick of a region in the sky. And what they saw was this. The Hubble Ultra Deep Field, almost every single smudge dot that you see in here is an entire galaxy that has hundreds of billions of stars in it. This is one tiny little, apparently blank spot of the sky, and this is what we found. There are galaxies everywhere in the universe, which is good, because it keeps me in a job. There's lots to study. But it's fascinating. So we've got this gorgeous image now. You can see some spiral structure over here. You can see really, really orange ones. You can see blue ones. There's little tiny red dots. There's bright blue ones. There's long, elongated ones. There are just an endless number of different types of galaxies in here. It doesn't even fit all the way into the Hubble tuning fork diagram. So now we've got this gorgeous image. What do you do with it? Well, you try to quantify things. You want to know how many spiral galaxies there are, how many red ones, how many blue ones, how many big ones, how many small ones, how many all of them. So you count them up, just to take a catalog, to see what are the most common. And then you want to know, how do they change? So do the red ones become blue ones, or do the blue ones become red ones, or do the spiral ones eventually become the elliptical ones? But in order to know anything about the evolution, you really have to know how far away they are. Because from this flat image, you can't tell which ones are close and which ones are far. And that brings me to one of the least trivial things in astronomy, is trying to figure out the distance to something. It's almost impossible sometimes. You imagine if you have a flashlight that's really close to you and you've got some spotlight that's really far away, to you, they might look exactly the same size, the same brightness. And unless you know that one's really far and one's close, you really can't tell just by how bright it looks. So determining the distance to things in astronomy is, in the universe is difficult. But we can do it. We do have some techniques. Oddly enough, it's almost easier to find things that are distant galaxies, to figure out how far they are, than it is to figure out the distance to things inside of our own galaxy. Just because there's different techniques. You can't use this technique on things within our own Milky Way galaxy. So I'm a bit of an advantage in that sense. So how do we find a distance to a galaxy? Well, we use a property of the galaxy that I like to call its rainbow fingerprint. Every galaxy has its own unique fingerprint that you can identify by taking a spectrum of it. So we look at this galaxy with a telescope, we collect its light off of our mirror, and we send it through a prism. Very expensive prism, but essentially it's just a prism. And you separate it into its rainbow. And you find little features in its rainbow. Ignore that bit for a minute. So this is one of these galaxy rainbows. It's got little features in it, these little dark lines. These are hydrogen. Of the normal stuff in the universe, hydrogen makes up about 90% of it. So hydrogen's a good thing to understand and look for and use as a tool. So this particular galaxy has these hydrogen lines, and you can see there's a very distinct pattern, a very distinct spacing between the lines. We can use that because these little photons of light, photons are the packets of light, the packets that light travels in. So some star in some distant galaxy is just doing its thing, nuclear fusion, emitting light, and those little photons of light are traveling to us at some wavelength. Now, little do they know, while they're traveling through space, the universe is expanding. And as space stretches out, it's actually stretching out the wavelength of that light. So if it starts at one wavelength, it actually gets stretched to longer wavelengths as it's innocently traveling to space towards us. So what we can do is we can say, well, we know exactly what the wavelength of this particular line is. And as that photon travels through space, that line gets stretched to longer wavelengths, to redder and redder wavelengths. So this entire pattern stays the same. It just gets shifted to longer wavelengths as all of these lines have been traveling for longer and longer and longer. So what we do is we compare some line to the line that we observe in the galaxy far, far away, and the distance between those tells us how long that light has been traveling, and therefore how far away that galaxy is, or at what point in time in the universe it actually emitted that light that is now traveling to us for us to catch. And we call this redshift, or travel time, or lots of different things. Redshift is, we denote it with a Z, and it's a unitless quantity, so 0 in redshift is today, and a redshift of 1 is about half the age of the universe ago. It's kind of an exponential. And a redshift of infinity is essentially the Big Bang. Nice confusing system, but we use it all the time. Okay, now we know how far away these galaxies are. I will give you an example. This is a rainbow fingerprint of a galaxy, this little spiral galaxy here. So this is essentially this rainbow that I showed you before, but now it's flipped. So it's two-dimensional, so you know how bright this red is relative to the blue. So that's what this extra dimension is. The black little wiggly things, that's the actual spectrum. That's the galaxy. And let's see, this x-axis, if anyone's interested, this is 4,000 angstroms. We use a strange unit called angstroms. But this is about the wavelength region that you can see with your eyes. So there's a whole lot more types of light that we can't detect with our eyes. But this is about what our eyes are sensitive to, and this is what a galaxy spectrum looks like. So you can see different dips over here and different spikes. These two black lines here represent hydrogen, so you can see the hydrogen is really strong. It's something we use quite a lot. There's some oxygen, there's a little bit of magnesium absorption from the stars in the galaxy. Some other things, if you look at the blue squiggly bit, that's what's actually coming out of the sky. So our atmosphere is also emitting things. In addition to absorbing light, it also emits light. So we've got all this noise in here from the sky, which is why we want to go up into the atmosphere. If we're up above the atmosphere and orbiting in space, we don't have to deal with any of that. Otherwise, it takes a long time from when I collect my galaxy data on the telescope to filter through all of that sky noise to get to the actual spectrum of what the galaxy looks like. So that's a whole process. We call it data reduction. It's the bane of our existence, but it has to be done. And eventually we can get some good science out of it. So I work for a project called GAMMA, which stands for Galaxy and Mass Assembly. This is what brought me to Australia. I work for the Australian, well, this is actually the Anglo-Australian Telescope, even though it's still the Australian Astronomical Observatory. It's all very confusing, these acronyms. So this is the dome where the AAT, the 4-meter telescope, lives. And this was us one night collecting spectra like this. With this telescope, you can collect about 400 spectra an hour. So it's a pretty powerful tool that we use out there. So this is the dome. The telescope lives inside of it. And we were having fun one night. I like to show this to my friends in the Northern Hemisphere because you can see the galaxy, and you can see the Southern Cross, and you can see the Coalsack Nebula there, that dark spot. So we were playing around with long exposure photographs, and I had a PhD student who was up on the catwalk who was practicing spelling his G backwards with his torch. The rest of the letters you're okay, you don't have to know how to do it, but G you have to go backwards. So over 3 minutes he kind of stood there and made these big letters. And I was down on the ground next to the camera making my big capital Gamma here with my laser pointer. And the other trick is that you also have to take your torch and really slowly illuminate the dome throughout the exposure, or else it's just silhouetted, and then it's not very exciting. So we get this photo, and we're really excited about it, and I go and I show it to the director of the observatory, and he really liked it, but he said, okay, first of all, green laser pointers are illegal in Australia. Just so you know, don't try to take it around with you. And number two, there's an absolutely clear sky here, and you have an open dome. why are you flashing a torch at it? But for this project, there's very limited part of the sky we can look at. So the dome's open, but it's looking over there, and there were clouds there, I promise. So we weren't wasting time. It was just fun. So now I'll give you a few gratuitous, pretty pictures of some observatories. So this is actually that 4-meter telescope inside of that big dome. Lives up near Coonabarabran. It's about 7 hours north of Sydney. This is the 4-meter telescope here. This thing is kind of over-engineered. Love these big, huge domes. This is actually the Spectrograph Views. So we collect, the light bounces off of this primary mirror and it goes back up there, and there's 400 optical fibers that collect light from individual galaxies. And then we send all those optical fibers down a couple floors in this building, and it pops out here, and it goes through the spectrograph. So there's different prisms and things in there. The light goes onto a CCD chip, sends it up to our computer, and we look at everything on the computer screen. So it's not really, we're not down there looking through our eyes anymore. The sensitivity isn't quite there with our eyes, so we have to use all this digital technology. So that's in Australia. Here's a few shots of the McDonald Observatory in West Texas. So this is where I did my PhD, and I spent probably 4 or 5 months, not consecutive, but out there at this telescope. So this is a 2.7-meter telescope, and it was actually constructed by an old submarine manufacturing company. So this big solid dome really felt like you were underwater, and there was massive machinery when this thing moved around. So this is the control room. You actually sit in a little room inside the dome, so you're not cold all night, but we're just set up with a bunch of computers operating the telescope from in there. This is me actually sitting on top of that. This is the dome that this telescope lives in. So this is me sitting on top of that dome, and there's another telescope off in the distance. That was not, don't tell the director of that observatory that I did that. He would not be very happy. And these were some wildfires that they had about 2 years ago that really threatened the observatory. In the end, nothing bad happened, but came out with some spectacular photos. Here is Chile. So this is about a 6-hour drive north of Santiago. These are the Andes Mountains. And I worked for about 8 months at the Gemini Telescope. So this is an 8-meter telescope. The mirror sits down here. It's 8 meters across. Here's the dome. The foxes hang out with you when you're up there, like that. And this is another image of Comet McNaught. So you can see the little town where I lived when I worked up at the observatory, and then there's the ocean back here. And finally, Hawaii, because I've got to show photos of Hawaii. So this is, the telescopes in Hawaii are built on this extinct volcano up here. So there's about a dozen, maybe more, major world facilities that live up on top of this volcano. And let's see, this is the Gemini's twin telescope. So there's one in Chile and there's one in Hawaii. And then there's a couple other telescopes there. This is one of the control rooms. You can see we've got a ridiculous number of monitors up there, but they all do their different tasks while we're observing for the night. And this is an all-sky camera. I like these because they're little fisheye cameras, so you can see the whole sky. But when you're observing, sometimes some of the telescopes use lasers. So they make fake stars with lasers, and they use that to clean up their images. But you can see these lasers shooting up into the sky, which I always like. Sometimes there's 2 telescopes that have lasers, and it's kind of a little Star Wars laser battle. Okay, so why do I bother traveling around the world using all these different telescopes? Granted, it's fun, and it's a nice perk of the job, but there are scientific reasons for doing it. We can get different bits of information about a galaxy based on the different kind of light we collect. When I showed you the spectrum before, it covered the wavelength region that our eyes are actually sensitive to. But there's a whole lot of other information that you can get from a galaxy. So this is M83, and this is, the blue light here is the ultraviolet. The green, or white, sort of down here is the optical. And then there's a little bit of red in here that's near infrared. So just by looking at this, you can see that the ultraviolet, which is a lot hotter, more energetic light, is distributed outside. You can kind of see some spiral arm structure. The optical is a bit more towards the center. So those are stars that aren't quite as hot. And then you've got the near-infrared light right in the center. So already, this isn't as much energetic light. So it's older stars. They're cooler. They're not quite as hot. Already we have that information, but if you go into the radio, look at the extent of that radio gas. It goes way farther out into the disk than we could ever see with any of the other types of light. And this actually tells us about the gas. the fuel that's in the galaxy, as opposed to the before, those were all stars. That's what stars were emitting. So what we can see with our eyes are the starlight, the things that illuminate our sky as stars. But there's all this gas everywhere that we can see through the radio. There's also lots of other things in the universe, like dark matter, that doesn't illuminate anything, so that's really hard to find. But we can play with the different kinds of wavelengths to really get a whole picture of what's happening in these galaxies. So now, we've got tons of galaxies. These are lots of examples of galaxies from the Gamma project that I work on. You can see they're not quite as pretty as our Hubble images, but I can gather 300,000 of these things, and I can take spectra of them at the telescope in Australia. So I have 300,000 galaxies with these images, and I know how far away they are. So this is a fantastic sample of galaxies that I can use to try to understand what they typically look like, and how they change over time, and how they grow up. And by grow up, I mean how they form stars, how they turn gas into stars. Stars like our sun that, might harbor some sort of life. So what have we actually seen? So I'm going to throw in a plot. It's not scary, but it's a plot. So this is time. This is from the Big Bang, so right at the beginning, all the way to today. The universe is about 14 billion years old now. And on the y-axis here is mass. So how much stuff is it? So what do galaxies look like over time? What we observe with our telescopes, what we see, is that galaxies now, when we look at them, the ones that are little, that don't have as much stuff, tend to be kind of blue and tend to have these little spiral arms. And galaxies that are big, that have a lot more stuff, tend to be red, and they tend to be those elliptical ones. Or they have these big bulges in their centers. Okay, so why would one be blue and one be red? We can actually use the stars in our night sky to understand that. This is the Orion constellation, upside down to some of us, maybe? I don't know. You can identify it by its 3 stars, the 3 stars in its belt here. Now, one thing you notice about Orion, or one thing I always notice, is, this is a bit exaggerated, but the stars are different colors. You can see that this one up here is very red, and this one down here is blue. The blue one is Rigel, and this is a very young, very hot, newborn star. And when it's really hot, it glows blue. This one up here is Betelgeuse, kind of an older guy, towards the end of his life, and he's getting cooler. So what happens when you cool off is you start to get red. So the color of a star is dependent on the temperature of the star. A lot of people will throw out its Doppler shift and it's how it's moving or how far away it is. Stars, that's not true. It's the temperature. That's what determines its color. So Betelgeuse, a fun fact, is it's very much towards the end of its life, but it's actually a pretty big star. So it might end its life as a supernova. So it could explode, and it could explode any time now. But in astronomical terms, that means like now in the next 20,000 years, maybe. But if it does explode, it'll be visible in the daytime sky for a little while, for a couple months maybe, which would be fantastic. So I am all for Betelgeuse exploding. But it's far enough away that it's not going to cause any damage, so conspiracy theorists, back off. It's okay. Right, so now imagine we've got an entire galaxy that has just undergone some star formation. So you've got lots of very young, very hot, very blue stars. If you look at all the light from those stars, all of it's going to look blue. So that's what these look like. If you've got old stars, galaxies whose stars formed a long time ago, they're all aging, they all look kind of red now. So the entire galaxy is going to look red because it's mostly these old stars. So what does it look like in the distant past? This is kind of what we see now in our local universe. Well, in the distant past, it turns out that it looks kind of the same. The most massive things that we see also look a bit red and look elliptical. And the younger things, or the lower mass, littler things, tend to have these spiral arms and disks. They look blue. So why might this happen? This is really getting at the kind of research that I do. So this is all because of the stars and when the stars inside the galaxy were born. So remember, these galaxies have hundreds of millions, hundreds of thousands of millions of stars, lots of stars. So you see the collective light of all of them. You don't see individual stars. You see the whole. So what happened in these big red things that we see today, when we look back in time, we see these really massive red things. And what happened is very early on in the history of the universe, they had this burst of star formation. So this is the star formation rate, the rate at which stars form. So you have this burst, all this gas all of a sudden turns into stars, and you get lots of light from these stars. Very powerful burst, but then it stops pretty immediately. No more stars are forming. And then the whole thing just ages over time. So all those stars that form just slowly age and get redder and redder and redder. So what we see today is a big red galaxy. As opposed to these little blue things. What we see with those little blue things is that this is still a bit of a mystery, but for some reason they don't form early on in the universe. They form a little bit later. Then they start forming stars, but they don't form quite as many stars. Their burst isn't as strong. But they form stars, and they actually form stars over a longer period of time. So they're just kind of piddling along, forming stars, and then they slowly stop forming stars. So when we look at them today, they still have a lot of young stars. So they still look blue, but they haven't formed as many stars, so they're not quite as big. Now, star formation didn't happen in two chunks. I don't want to give you that idea. This is a continuous process. So early on, these galaxies were booming and booming and forming stars, and then they kind of slowly, gradually declined in the amount of stars that they were forming. So today, fewer galaxies are forming stars, and those that are forming stars are smaller. And if you look at any given time, the ones that are forming the most stars tend to be these spirally disky things, and the ones that aren't forming as many stars are these red elliptical-looking things. Okay, so this is what I see with my telescopes. So the next stage is to try to understand theoretically what might be happening. So we want to use our physics as we think we know it, and try to go from observations to recreating these galaxies that we see with our telescopes. To do that, we start with our universe's baby picture. That's essentially what this is. This is called the cosmic microwave background radiation. And this is everywhere in the sky. So just like when you see projected maps of the Earth in this kind of elliptical shape, it's just a way you project the sky. So everywhere in the universe, this is the first light we know how to detect after the Big Bang. This is when the universe is about 300,000 years old. And you can see the universe over here looks pretty similar to the universe over there, which is a good thing. There's no preferred direction. If you go far enough that way, you'll get to pretty much the same thing as you get to if you go that way. But you do see some difference. So you've got red down to blue. And those differences are differences in temperature that we can measure. But very, very small differences in temperature. So the red might be like 10,000 and the blue might be 10,001. So very, very, very small difference. But it's a good thing those differences were there, because that difference in temperature meant a difference in density. And because there was a difference in the amount of stuff, gravity started to act. And gravity caused different little gas clouds to collapse. And because of this conservation of angular momentum, those gas clouds collapsed and started spinning and started forming galaxies. So then we had these galaxies forming stars, and there were supermassive black holes, and supernova exploding, and galaxies crashing into each other, all sorts of exciting stuff, and out pops the Hubble diagram at the end. So really what my research is trying to figure out how we go from this to that. Small task, but I'm trying. Okay, so how do we understand this theoretically? We start with something that we think we might know a little bit, like gravity. I mean, I know I'm going to come back to the Earth if I jump. So gravity is pretty well understood in that sense. So let's start with a model. This is just some big box of particles that are evenly distributed, sort of like they were in the cosmic microwave background radiation. We let this go under the force of gravity. That's the only thing that's reacting. You see this Z, this is redshift, so it starts a very long time ago, and we watch it evolve over time and see what happens. And you see that even distribution of particles starts to collapse, condense under the force of gravity, and clump up in certain regions. So you see almost this filamentary structure that forms. You get a lot of particles in certain regions, and then you get these nice open spaces in other regions. And these correspond to galaxies that we see. So each little dot might be some clump of galaxies. So you get these huge clusters, groups of galaxies, and then you get these open spaces where there aren't so many galaxies. Compare that with what we see with our telescopes. So this is a view of the sky. If you imagine us at the center, and you take a telescope and you just point it over a big strip of the sky, and you put a dot everywhere you see a galaxy. So the open regions are places we haven't looked at with the telescope yet. But this is what our sky looks like, according to a big survey called the Sloan Digital Sky Survey. Now, if we compare those two, you actually see that they do a pretty good job of agreeing. You see this filamentary structure in our simulations, and you see this nice filamentary structure in the universe as we see it. So the distributions of galaxies are pretty well matched from our computer simulations and what we observe. This brings me to another of my favorite big things, little things in the universe. So this is what you call the large-scale structure, this filamentary structure that happens in the galaxies, like I showed you in that simulation. Big clump here, and then these little filaments connect these other little clumps. It's amazingly similar to what a brain cell looks like. If you look at these little synapses that happen in our brain, it's a very similar filamentary structure. Completely different scales, completely different times, but it's another one of these fascinating things. Okay, so let's look at one region of the sky. These are footprints of where we actually look with our telescope. It's about 4 degrees and lots of degrees this way. And I put a picture of the moon so you get an idea of how big it actually is on the sky, but really the moon is more like that. So these are actually pretty big chunks of the sky that we look at and try to get all those galaxies. Remember, the Hubble Ultra Deep Field was smaller than my laser pointers area in here. So these are actually huge amounts of sky, and now you know why I can get 300,000 galaxies out of these surveys. So this is all of those surveys, but now we are right here at the bottom, and we're looking back in time. So these are redshifts from point 3 to point 4, and these are lookback times, so billions of years. So 1, 2, 3, all the way to 5 billion years ago. And there's a dot everywhere, there's a galaxy. And I'm doing this just to show all these different surveys, all these different telescopes are still seeing this filamentary structure. It's not like it's only in one direction. So everywhere we look, we're seeing this nice filamentary structure. So our models, our simulations based on gravity, are pretty successful in recreating the distributions of galaxies as we see them with our telescope. This is a huge success, a match between theory and observation. But the problem comes when you look at any one individual clump, and then you look at it through the telescope. You see all of this light produced by stars that interact electromagnetically, gas that interacts thermodynamically. These processes are very difficult to model. It's much more complicated than just throwing in gravity. So essentially everything that happens over this 10 billion year period, everything that happens between the stars and the gas and the thermodynamics, all of that is very complicated to model and very complicated to understand. So we're trying, but this is a pretty tough thing to do. So unfortunately, to come back to this plot, we can't look at one individual galaxy. As I said before, they take so long for anything to happen. You can't just sit there and watch that one galaxy evolve, unfortunately. But probably what happens in that one galaxy is it gets some initial spike of star formation, and then maybe it slows down, and then maybe something happens to it, and it gets a lot more gas, more fuel, and it can form more stars, so it gets another peak. Maybe it slows down because the supermassive black hole in the center decides to go off and puts a lot of energy into the system and slows down its star formation, so it dips. So up and down, all these little things happen to individual galaxies. But overall, if we look at lots of them and try to get a statistical idea of generally what's the most common thing that's happening, we do still see this pattern where the star formation behavior, the way galaxies grow up, changes over time. And what my research in particular has shown recently is that the smallest galaxies have these really old populations of stars, and then they've got other little bursts later on. So what I've been showing is that the smallest things that you see, what we call dwarf galaxies, or little things, they had a little burst way long ago, but then they stopped. Kind of a mystery, we're not really sure why. And then they started again and had a little burst and then stopped. So they had a lot more bursty behavior than these nice, smooth curves here. So that's the stuff I'm working on. But I'm going to change gears for the end of the talk and introduce this woman who is huge in my field of research. And unfortunately, I cannot find a better photo of her. You'd think there'd be one now, but this must be from the 90s or something. To write to her and say, you need a better photo. Anyway, Sandy Faber is huge in this field of galaxy evolution, and I bring her up because about 30 years ago, she gave a talk at the American Astronomical Society meeting, which is one of the biggest meetings of professional astronomers in the world. She spent an hour trying to convince astronomers that galaxies don't live isolated lives. They don't live just by themselves. They actually interact with other things around them. And in fact, galaxies can come together, get stuck together by gravity, and eventually merge into single systems. So 30 years ago, we had no idea that this happened. We didn't really see it. We didn't really see too many galaxies. Now I'm looking at hundreds of thousands. But at the time, we couldn't find them that quickly. So that's what her argument was 30 years ago. And thanks to Hubble, we can see amazing examples that, yes, indeed, this does happen. You can see here, these two galaxies are still far away. They still have a nice spiral structure. These two have actually crossed paths, so they kind of get all distorted, and stars go flying. Later on, you can see these spiral arms just get shot out, stars get flung. They get completely disrupted, and then eventually they sort of come together and form one galaxy at the end. But a galaxy merger, you might imagine like fireworks and big explosions happening, things crashing into each other, but that's not really what happens at all. It turns out that the distance between individual stars is so big that when galaxies merge together, almost never do stars actually hit. They just sort of pass through each other. But they're fundamentally driven by the gravity. So the gravity, you imagine it's like a little ball. That gravity is going to slowly bring these things together. They don't have an up or a down. So the gravity is definitely more three-dimensional than what our intuition tells us. So I've got a movie to demonstrate this, if I can get a hold of it. This is a simulation of two different galaxies crashing together. So this is a computer simulation. Right now we're just looking at the gas. So it interacts thermodynamically. You can see the temperature differences in the gas based on the color here. You can see this wing of gas gets strung out during this interaction. But slowly, these two centers are stuck together by gravity, so they slowly come together and eventually form this one system. So you can see the gas actually has these really crazy reactions when it gets heated up. You can see the central bit is spinning here. And this is time, so this is 2,000 million years, so 2 billion years here. This is a pretty interesting system. So now we're looking at just the stars. So not the gas, but just the stars. Stars don't behave in the same way. So they just interact with each other through gravity. You can still see these things getting flung out here, but the central regions lose a bit of energy in that first pass and slowly, slowly fall towards each other. You can see the colors here represent the age of the star. So the old ones all kind of sink into the center of these two systems. And eventually they fall in. You can see different stages, evidence of spiral arms. But eventually they fall in and they form one kind of chaotic system that eventually forms an elliptical system. And over time, if nothing happens, then maybe slowly it starts spinning and maybe starts to form a disk again. But after this interaction, it's nice, chaotic. Stars are going in all kinds of directions. So this is the gas from two different angles and the stars interacting from two different angles during this merger. This is ultimately what's going to happen with the Milky Way galaxy and the Andromeda galaxy. Not to scare you, it's not going to be for 4 billion years or so. But this is what's going to happen. Right now, they're stuck by gravity. They're essentially orbiting around each other very slowly, but they're getting closer and closer and closer. And eventually we'll be able to see the Andromeda, well, we won't, but, somebody in our galaxy will be able to see the Milky Way, or the Andromeda galaxy, the spiral galaxy, getting closer and closer in our sky. Right now you can see it a little bit. It's a little smudge if you know exactly where to look. But it'll get closer and closer and closer until it takes up our whole sky, and then you can see them interact. Now, there's no way to predict where any one individual star is going to go in a process like that. So, unfortunately, we can't really tell where our sun's going to go or where our Earth's going to go. So we might get flung out, or we might just get sent to the center of that system. But again, it's not for another 4 billion years, so nobody needs to worry about that. So another simulation, another aspect of simulations that are difficult is you can, in that big volume, that blue volume I showed you before, each one of those points would be like an individual galaxy. And it just interacts through gravity. So that's a pretty complicated simulation. You have to take, say, one galaxy, and you've got all of its nearest neighbors, and you stop in time, and you calculate the force of gravity from everywhere. And you say, okay, this guy's going to make me move this way and this way. So you do the calculation, and then you let them all move, and then you stop again in time, and then you do all the calculations again. And everybody moves, and you stop again, and you do the calculation again. And that's what's happening through that whole thing. So, I mean, it takes a bit of computing power, but gravity's not too difficult. Now, if you go and you add in gas, which has all these other properties, and you add in stars, which have different properties, and gravity, you can imagine it takes a lot of computing power. So you can't do lots of different galaxies at once. What we're trying to do, well, we've tried, it just doesn't work. You can't fine-tune, you can't add all the physics that you know into it. And so you know that you're missing physics, and then your galaxies look all wrong at the end. So what you try to do is try to fit individual galaxies. So this is an observed galaxy, this is M87. So this is just one example of a nice spiral galaxy. And this is what this galaxy might look like from the edge. So if you looked at it from the bottom, you'd see this nice disk. This is actually the Milky Way, from our point of view, looking through it. So one thing that has been really hard to create through computer simulations are these flat galaxies. So disk galaxies that are very flat. We can do the spiral ones pretty well, but it seems to be a lot more difficult to get them as flat as they are. You get them kind of flat. To get them really flat is a pretty difficult thing in these simulations. So recently, just about a year ago now actually, this simulation came out called ERIS. And this was a simulation that took 8 months to run in Europe on one of the world's biggest supercomputers. They added in every bit of physics that they could to this. So when a star exploded, they would figure out exactly what sort of effect it had on the gas around it. They had supermassive black holes, they had gas, they had stars forming. So the most detailed simulation took 8 months to run, and I'll show you the result of that simulation. The goal was to try to create a galaxy that had a flat disk. So it starts out as a cloud of gas. It starts out really early, so there's lots of different things that are all interacting over time. So you can see little things coming in and crashing in, so the universe was a bit more dense back there, so we've got all these things coming in and crashing together. We're looking from the top end, so we start to see finally the formation of spiral arms, as they'll tell you. I'll read it. About 100 billion years ago, there's the last major merger of galaxies. So 100 billion, or 10 billion, the universe is about 14 billion. After this, we can see the disk of the spiral galaxy starting to form. You can see the spiral arms. So not so many mergers anymore, a couple there, but now we're settling into the structure. And we're starting to see chunks of things falling in. Not all of these are visible to our eyes, so we can't see them all when we look. But each time step here is hundreds of millions of years. So this isn't anything that we can see happening with our telescopes. This is something we can only infer from these simulations. So now we're about as wide as the Milky Way galaxy is, 100,000 years. You still see things passing through. You know that we have the large and small Magellanic Clouds. These are like examples of little clumps that are gravitationally bound to the Milky Way that will eventually fall into the Milky Way. They'll become part of it. So now the galaxy begins to resemble the Milky Way and grows more slowly by accreting gas and dwarf galaxies. So we will accrete the large and small Magellanic Clouds eventually. And it'll shake us up a little bit, but it'll do a lot more damage to them than it will to us, because we're just a bigger, more gravitationally powerful system. And at the end, what we see after 10 billion years of evolution is that we can find a galaxy. We can form this galaxy that has the spiral arms. It has about the width of the Milky Way. And it only took a measly 8 months of supercomputing power. Let's see. Ooh. So the results from that simulation are these. And you can see they actually do a pretty good job of recreating the observations that we have. A little bit of investment in computing power. Okay, before I end, I would like to just do a couple advertisements if you guys are interested in seeing more stuff. There's a project out of the University of Nottingham by this guy called Brady Heron, Deep Sky Videos. He's done a video for, well, he's doing in the process of doing a video for each of the Messier objects, and then as things come up in the news, he does different interviews. He interviews the professors and people working at the University of Nottingham. I was involved in this project a little bit when I was there, so I pop up in some of these videos. The one I was in mostly was 60 symbols, and it's still going on now, but it's not as rapid anymore. So these are videos of the symbols of physics and astronomy. So you've got the speed of light, and let's see, Schrodinger's cat, and pi, and what's a gigayear, and there's a vuvuzela, the physics of that, if anybody remembers that during the World Cup. This was a total solar eclipse. I was lucky enough to get to go to China to see the solar eclipse, and I'm going to go in November again to see the one in Cannes. Very excited about that. There's a whole section on solar system objects, so if you're interested in anything about planets or asteroids, you can go check those out. That one's 60symbols.com. If you want to do a little bit more interactive stuff, you can go check out the Zooniverse. They've got lots of different projects where you can actually go and look at data and try to find stars, try to find planets around stars. The Galaxies Zoo, you can go and look at galaxies. You can identify if they've got spiral arms, if they're blue, if they're red, if they've got funky stuff happening with them. Lots of gorgeous images. The Hubble images are thrown in there too, so you can look through Hubble. Explore the surface of the moon. You can look for stars forming inside of our own galaxy. And I think that's all the advertisements I have. So I'd just like to say thank you very much for your attention, and I'll take any questions if you'd like.